I would like to show you here a simple application of linear algebra to circuit analysis. I want to demonstrate the methodology based on very specific circuit which you see here on that page. But the same technique will work with any circuit, even if you have, instead of resistors, you have impedances, or you have any other structure, or you have much more sophisticated circuit with more loops, and so on. So our first step, which I will outline here, is drawing n loop currents in clockwise direction. So draw n loop currents in clockwise direction. So let's do that. Let's say this is our loop number 1, and we're doing that in clockwise. So we will select I1 here. This will be our loop number 2, and you'll say this is I2, and the third loop is here, and this is the direction, which is also clockwise. Now step number 2, write a matrix This matrix, we will call it R, and the dimensions of that matrix will be n by n. Pay attention that n is number of loops that we have. So let's start doing that. So since we have 3 loops, the matrix will be 3 by 3. So let's draw it here. This matrix will be 3 elements, 3 rows by 3 columns. Next step, step number 3, is fill the main diagonal RII. So what we need to put in the main diagonal? Those are the elements of main diagonal, and we have 3 of those, because totally the matrix is 3 by 3. So this is basically R11, this is R22, this is R33. So we need to fill it with sums of all resistors in the loop I. Now, let's see what it means. In the first loop, here, we have one resistor, second resistor, and third resistor, which means we're adding all of them together. One is 1 kilo ohm, 4 kilo ohm, and 2 kilo ohm. So, inside of the matrix, what we will have is basically 1 plus 4 plus 2, which is 7 kilo. Similarly, for the second loop, we have 5 kilo ohm, 4 kilo ohm, and 6 kilo ohm. So it's 5, 4, and 6, which will give us basically 15 kilo ohm. Loop number 3, so it's for R33, we have 2 kilo ohm, 5 kilo ohm, and 3 kilo ohm along the loop, which means it should have 7 plus 3, which is 10 kilo ohm. So we completed the main diagonal here. Okay, next step, number 4, we need to complete all of the other parts of the matrix. So Rij, where I is not equal to j, will be minus, and common resistors to the loops I and j. which means we are looking, for example, at loop 1 and 2, and we see that common resistor is that one, because it's between loop 1 and loop 2. So this is R4, which is 4 kilo ohm. We need to put it with minus sign. Now, this matrix will be symmetrical, which means that Ij and Ji will give you exactly the same value of the resistor, which means that we need to put that value of minus 4k in two spaces. One is here, and one is there. Because this location here is basically 1, 2, and this location here is 2, 1. So it's between I and J, which are 2 or 1. Now, the same thing we are doing for all other loops. So, how about this place here? So this place is 1, 3. Between loop 1 and 3, we have only R2, which is 2 kilo ohm. So we are writing there minus 2k. Similarly, here we need to write minus 2k for symmetricity. And the last one is between loop 2 and 3. So it's second row, third column. And we get the only one is R5, which is 5 kilo ohm. So it's minus 5k. And here also minus 5k. So we completed that matrix that we wanted. And the last step, step number 5, we need to write vector of voltages in the loop I. Now, it's very important in which direction you write that voltage. So here we will write that vector. The size of that vector will be exactly the size of the matrix, which is 3, but the second dimension will be 1, because this is a vector. So it's 3 by 1 column vector. In that vector, we will write voltages in the loop 1, loop number 2, and loop number 3. So we will have 3 different elements. Now, if the current moving with the sign of the voltage, we will put it as positive voltage. So for example, in the first loop, the only source of voltage is V1, and this voltage is coming in the direction of the current, I1, which means that we will have here 10 volts. Second loop, you don't have any voltage sources, so you don't have any voltage, which means you need to put 0. And then the third loop includes 15, but current flows that way, and 15 shows that way, which means you need to take it with negative sign. So it's minus 15 volts. That's it. We completed all of the systems that we wanted. So we will call that matrix R, and that vector V. The only thing we need to add is to multiply that matrix by matrix of I1, I2, and I3, and to put equal sign. This system should be correct for any circuit you analyze. Now, how you solve it? So technically you have basically system of equations, which is R multiplied, if you call that thing I, which is not a good name because this is vector I and not identity matrix. It will be equal to vector V. To solve that equation, we saw already that all we need to do is to find I vector as R inverse multiplied by V. You can do that in MATLAB, and this is what you'll get. You'll get that I1, I2, I3. Then you're multiplying those two things which are given, because this is constant matrix and this is constant vector, so all the numbers are given. This is what you get. You get values 0.87, minus 0.25, and minus 1.45. multiply it by 10 minus 3, 10 minus 3, and 10 minus 3, which gives us just values of milliampere. So it's 0.87 milliampere, minus 0.25 milliampere, and minus 1.45 milliampere. So based on those values of those mesh currents, we can identify all of the voltages in the circuit, all of the currents in the circuit, and so on. For example, if you want current through that resistor, you're just taking I1 going that way minus I3 going that way. So just take I1 minus I3 and you will get current through that resistor R2, and so on. So you can find basically voltages and currents on every single resistor. If you replace it with impedances, if you want to add capacitors or any other elements, you can do the same technique to find voltages and currents in the circuit.